These are notes 5, 6, something you all love, word problems. Basically just giving you equations and working them out though, just solving the equations, okay? So knowing to read it and then plug them in, where to plug in is the important part. Okay, so we're going to talk about exponential growth function and exponential decay functions. Basically, this says we start with a certain amount and it's either going to grow exponentially, or we start at a certain amount, or a sub o, and it's going to decay exponentially. Okay, so we have those two different types of equations. So the first problem we have here is maybe one that you've seen before with earth science, but carbon-14 is a radioactive form of a carbon that is found in all living plants and animals. After they die, the radiocarbon disintegrates. Using carbon dating, scientists determine the age of the remaining by comparing the amount of carbon-14 present with the amount found when it was living. So the amount of carbon-14 after t years is given by this equation right here. So you can see that this is the decay function, right? So we start with a certain amount and it decays over time, with our constant being this one. Because our half-life, we have half the life of the substance left, is 5,700 years. If a fossil contains 1/5 of the carbon that it contains when it was living, estimate its age. Okay, so by using this equation, our end amount, okay, our end amount here is 1/5 of what we started with. Okay, and equals a sub o times e to the negative, and we know that this k is this number right here, right? That's our k there. So natural log of 2 over 5,700 times t. Okay. So if you think about this, I'm going to divide by a sub o on both sides. They just kind of cancel out, right? So I have 1/5 is equal to e to the negative ln2 natural log of 2 over this times t. The way that we solve these e problems was we take the natural log of both sides. So natural log of both sides. On this side I have the natural log of 1/5. And over here those two cancel out. So I just have negative natural log of 2 over 5,700 years times t. And then to get t by itself, I got to take this and move it over the other side. Okay, so I'm going to multiply by the inverse of it. So it'd be this over this times natural log of 1/5. And if you would put this into your calculator, into Desmos, you get t is equal to approximately 13,235 years. Okay, so if it contains 1/5 of what it had contained before when it was living, it's over 13,000 years old, is what this theory says. Okay. Radium 226 decays by this equation, same equation here, where t is the time in years, and it has a half-life of 1,612 years. Find the exact value of our k. Okay, so it's a half-life. So the amount that we have in the end is 1/2 of what we started with, right? So this is what we start with. This is what we have in the end, half of it. And we continue with it, e negative k, which we want to find, and 1612 is the half-life, right? So half of it is gone in this amount of time. Okay, so we got to solve this. I would divide by a of o both sides. Okay, get rid of the e by taking the natural log of both sides. So I have natural log of 1/2, and that's really just negative 1612k. And to get k by itself, I'm going to divide then. So natural log of 1/2 divided by negative 1612, which is approximately 0.00043. Okay. So that is that k function, and we can see how it decays. Number 3, the loudness of sounds is measured in a unit called decibels. To measure this, we first assign an intensity, I sub O, to a very faint sound. That's our initial, that's what we start with, called the threshold sound. If a particular sound has intensity I, then the decibel rating is the decibel is equal to 10 log intensity over what the intensity was, the threshold. In the Lord of the Rings action sequence, the decibel is reached 10 raised to the 9.5 of what the threshold was, the original. Find the decibel rating of this compared to the average rating of 80 decibels for a telephone ring. So we're going to compare it, how much louder was it than a telephone ring. Okay, so we're going to use this equation here. So we know D is equal to 10 log, and the intensity here is this, so 10 to the 9.5 I sub O divided by I sub O. Okay, so when working this out, this just cancels out, so we just have 10 log base 10, right, of 10 to the 9.5. So since this is base 10, right, okay, remember we had that one in section 3, we had those 6 properties. One of those properties we're using here. So this would just be 10, those cancel out, times 9.5, which is 95. Okay, so it reaches a sequences of 95 decibels. Okay, now if I want to compare that to the other, to this telephone, okay, so now I'm going to compare to the telephone. I have 10 to the 9.5 IO divided by 10 to the 8 IO, 80 decibels. This gives you, those cancel out, 10 to the 1.5, which is approximately 31.6, which means this action sequences are 31.6 times more intense than an average telephone ring. Okay. Number 4, how long will it take $1,000 invested at 6% interest compounded quarterly to grow to $2,700? Okay, so if you remember, this is the equation we used back a couple days ago when it was compounded quarterly or monthly or daily. Okay, if it's continuously, then we use the E, right? But this is if it's this, okay? So we want it to equal $2,700, and we put $1,000 in. Our rate was 0.06. Quarterly is 4 times per year, and we want to solve for the T. Okay, so we just want to solve all this out. First I would divide by this 1,000 there, so I'd have 2.7. Okay, I'm going to take the log of both sides. So yeah, so I'd have log of 2.7. Okay, now if I use this, the power rule here, I can bring that to 4t out front. Okay, so power rule, take log of this, bring it out front. Okay, now to get t by itself, I'm just going to divide by this other stuff. Okay, so I have log of 2.7 divided by, I'm dividing by the 4, and by the log of 1 plus 0.06 over 4. Okay, and if I work that out, put this into Desmos, comes up to be about 16.68. Okay, so it takes over 16 and a half years for this $1,000 to grow into $2,700. Okay, what if it's compounded continuously? Okay, so notice in it's compounded continuously, we're going to use a different equation. We had that equation. Okay, so we want it to double. So we want this our amount at the end to be double this one, right? So we want it to be 2p if this one's p at a rate of 3%, and we want to know how long, so that's the t we're solving for. Okay, so what I would do is I'd divide both sides by p. We get this. Inverse of e is natural log, so I'm going to take the natural log of both sides. Natural log of 2 is equal to 0.03t, and divide by 0.03, and you get approximately 23.1 years. Okay, so in 23.1 years it will double. Okay, that's cars. You purchase a car for $24,000. You have a down payment of $4,000, so that means you owe $20,000 more yet. And you take out a loan for the remaining balance that will be paid in 36 monthly payments at 8.5%. Find the amount of each payment. Then find how much interest you'll pay over those years. Okay, so we have to have this right here for us first. Okay, so this stuff right here, the loan of dollars at an interest rate of I per period may be amortized in n equal periods. So okay, so this is how they figure up your car loan, okay, or your mortgage or other things. Okay, so the R, which is the payment of our dollars, so how much we have to pay every month, is equal to how much we owe. Okay, so in this case over here we're owing $20,000, right? And divided by this right here, 1 minus, yeah, this is the interest we owe and all that. Okay, so to plug these numbers into here, our monthly payment is going to equal, we bought it for $24,000, but we already paid $4,000 down payment, so we owe $20,000. We have 1 minus 1 plus, okay, the interest here is the interest rate per period. Okay, I said was the interest rate per period. So if we take this 0.085 and divide it by 12, because it's monthly payments, that's what the number is going to be right there. And to the end payment, so we're going to take 36 payments over 3 years, so negative 36. Okay, and the whole thing here divided by this I again, which was 0.085 divided by 12. Okay, looks like a fun equation to figure up your monthly payments, right? Okay, so yeah, if you just type this on the Desmos here, it'll come up to be approximately $631.35. That is how much your car loan will be every month for 3 years if it's at 8.5% and you owe $20,000. Okay. To find how much interest, so this is what we could do to find the interest. So we would pay I, interest, is equal to is how much we've paid out minus how much we owed, right? So what we paid out for 36 months, we paid out $631.35. Okay, so if you multiply that together, let me get my calculator real quick. Okay, for 36 months, if you pay that much per month, you've paid $22,728.60. And what we owed was $20,000, right? So you subtract those two, and you've paid $2,728.60. Okay? Now, ideally, if I was you, I'd try and save up more money before I buy an expensive car. Try and make more of a down payment so you don't have to pay so much interest over 3 years. Think about that. that's over $900 every year you're paying in interest. So that's a lot of money when you have to borrow money from a company. Number 7, world population in billions of dollars world population in billions of people during year X, so a certain year, can be modeled by this equation. What is the population predicted to reach? When is it expected to reach 7 billion? So we want our population to be 7 billion. Okay, so to solve this, I would first divide by the 3. And we can take the log of both sides. So we have log of 7/3 equals, okay, and yeah, the log of 1.017 raised to the x minus 1960. Okay, now we're going to use the power rule, bring that out front. This would be x minus 1960 times this. Okay, we can take this and we can distribute it through. So this would be x log of 1.017 minus 1960 times the log of 1.017. And to get x by itself, I'm going to add this stuff over and then divide by this. Okay, so x is going to equal log of 7/3 plus 1960 log of 1.017 divided by the log of 1.017, which is approximately the year 2010.3. So a third of the way through the year 2010 is where it would have expected to be 7 billion people. I just looked up on Desmos, and it's about 7.6 billion people right now. Okay. Future concentration of CO2 are shown in the table. X equals 0 corresponds to the year 2000. CO2 is what's harming the ozone and so forth, right? So use Desmos to find the exponential growth equation that fits the data. Predict for the year 2025 then. Okay. And also over here we're going to use Desmos as well, so I'm going to make a separate video, patch it in here, of using Desmos how to do this. But these are those 2 problems right there. Okay, for number 8 in the notes, talking about the CO2 concentrations, we want to make a table of values here, and then we're going to find the equation. So I'll pause this video as I put the numbers in. Okay, the problem did say that x equals 0 corresponds to the year 2000. So this is the year 2000, 2050, etc. Okay, so to get an equation for exponential, we're going to hit that y1 tilde. Then it's some number, we'll just call A, and some number we'll call B, and it's raised to the x. Okay, x1, right? Okay, so remember y1, x1 up here. So here's our model. It has our equation of y equals 364.113 times 1.005 to the x. Okay, so we can see by that equation, remember our equation's like 1 plus something, right? It's increasing by that much every year, okay? The percentage, it's increasing because this is above 1 as well, right? Remember, if this number is above 1, it's an increase. If it's between 0 and 1, it's a decrease, okay? Now, if we want to make a prediction for the year 2025, that means x is 25, so right in here, what would 25 be, right? So I'm going to say, what is 364.113? I'm going to plug in my time. My x is 2025. So it should be about 412.47. Okay, and that kind of makes sense, halfway between there. Okay, 412.47. Okay, good. Okay, so the next one, it says a table lists the interest rates for a CD in January 2005. So So I'm going to make a table again and put in the interest rates for a 1-year CD or a 2-year, 3-year, 4-year, or 5-year. I'll pause and put those numbers in. Okay, and putting those numbers in there, you get this graph. Okay, so the first question I asked there is what function is most appropriate? You can see the pattern kind of like this. So it's a log function. Okay, it's a type of log function. And the second part of my question I asked was to get the equation in the form of a plus b natural log of x. Okay, so this is how we get that equation. So y1 tilde a plus b natural log of x1. Okay, so you can see that fits the data fairly well. But our equation would be y equals 2.24 repeating plus 0.826 natural log of x. Okay, so that's the equation there. And that's the end of the notes.